Hello everyone and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into a really interesting paper called SAM2-MOT, a novel paradigm of multi-object tracking by segmentation. So, the core idea here is taking the segment anything to model, which is great for single object tracking, and extending it to track multiple objects simultaneously. They propose this new paradigm called tracking by segmentation, which directly generates tracking boxes from segmentation masks. This is pretty neat because it makes it less dependent on traditional object detectors and allows for zero-shot generalization, meaning it can work across different datasets without needing specific fine-tuning. Okay, so let's look at Figure 1 here. This chart compares SAM2-MOT with several other multi-object trackers on the DanceTrack dataset. The horizontal axis shows the HOTA score, and the vertical axis shows the IDF1 score. Basically, higher is better for both. The size of the circle for each tracker represents its ASA score, so a bigger circle means better association ability. You can see SAM2-MOT. That orange circle in the top right is clearly leading the pack with really high HOTA and IDF1 scores and a large circle size. And notice the color. Orange means it doesn't need fine-tuning for the detector or specific training for the tracker, which really highlights that zero-shot capability we talked about earlier. It's significantly ahead of other methods shown here. Okay, so building on that performance we saw, Figure 2 gives us a nice overview of how SAM2-MOT actually works under the hood. You can see the video sequence goes in, and a detector provides initial prompts. These prompts kick off the SAM2 trackers, which generate segmentation masks. Now, the clever parts are these two new modules they introduced, the Trajectory Manager System, which handles adding and removing objects and reconstructing their quality, and the Cross-Object Interaction module, which deals with things like occlusions. These feed into a memory bank, and ultimately, the system outputs the bounding boxes for tracking. Part B of the figure just visually reinforces that zero-shot idea, showing the detector assists, but the tracker itself doesn't need fine-tuning for specific domain data. Okay, so building on that overall architecture, Figure 3 zooms right into that cross-object interaction module we touched on. This shows how it specifically deals with occlusions. When objects block each other. See how it detects when the mask overlap, the MIOU, gets high, over 0.8 here. It then uses the logit scores and compares their variance over recent frames to figure out which object is actually hidden. Once it identifies the occluded one, it removes its memory entry for the current frame 11 in this diagram, preventing that error from messing up future tracking. So, after looking at how it handles tricky situations like occlusions, let's see the hard numbers in Table 1. This table lines up SAM2-MOT against a bunch of other popular trackers, specifically on the DanceTrack test set. It shows several key metrics like OTA, MOTA, IDF1, and ASA. Higher is better for all of these. Look at the bottom two rows for SAM2-MOT, using different detectors but, importantly, with no fine-tuning. It hits a 75.8 HOTA and a really impressive 83.9 IDF1. These scores, well, they clearly outperform the other methods listed, significantly surpassing previous state-of-the-art results, especially highlighting its superior association ability on this tough dataset. Okay, so building on those strong DanceTrack results from Table 1, Table 7 here gives us an ablation study, basically showing how much each part of SAM2-MOT contributes to that performance. Still, on the DanceTrack test set, we see a baseline score, and then results as they add key components, like the object addition strategy, the cross-object interaction module we talked about, and the quality reconstruction mechanism. You can see as each part is added, represented by the check marks, the HOTA, MOTA, and IDF1 scores consistently improve for both detectors tested. The paper notes that the cross-object interaction module, that COI column, provided the biggest jump in performance, especially for association metrics. Alright, so after seeing how the individual components boost SAM2-MOT's metrics, Figure 4 gives us a visual comparison against another method, ByteTrack. Across those different datasets we mentioned, DanceTrack BDD100K, and UAVDT. You can see ByteTrack just uses bounding boxes, while SAM2MOT also shows those colored segmentation masks. Well, looking at these examples, especially in the tricky dance track scene with occlusions and the crowded car scenes, SAM2MOT appears to maintain object identities more consistently, visually backing up those strong association scores we saw earlier. So yeah, those visual comparisons really drive home the point. SAM2MOT's approach of tracking by segmentation, it really seems effective, especially in handling those tricky occlusions and maintaining object identity, giving it that state-of-the-art association accuracy we saw. This really pushes forward how we think about multi-object tracking, moving beyond just boxes toward richer representations. Well, that's all the time we have for today. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.